Okay, let's now look at Pytorch and how we do the backpropagation computation. So we showed that previously in part 2 we could have a very simple network configured with these two inputs, F1, F2 on the input layer and the output layer function F3, and we could express this very simply as some straightforward Python code, 4 lines of code, including our error function, which is z minus y squared divided by 2, our mean square error. So now, first of all, we configure the input values for our actual data sample. So nominally, we're going to make these the same as we had in part 2, as when we were doing the algebraic expression, where the parameters S1, S2, S3 are set to 1. In actual, ordinarily, for gradient descent, these will be randomized. And the inputs are 2 and 3, and our target variable is 1. So then to connect this up in terms of Pytorch, we would first of all import torch as to the Pytorch library, and then we would express these values as Pytorch tensors. So this data type, torch.tensor, allows us to declare an arbitrary tensor of any size. We're here obviously using them as scalar values for our example, and we'll talk later on how using tensors would actually make no difference to the backpropagation method. And then look how we declare the variables straightforwardly using these data types, but for the S1, S2 and S3, which are our parameters that parameterize our function, we set this requires grad equals true. This is telling Pytorch, be prepared to accumulate the gradients for these variables. In other words, we want to compute the final output of our error function with respect to these 3 variables, and Pytorch is being instructed to use those 3 variables as the inputs that we want to accumulate gradients for. So first of all, we do the forward pass and we can inspect these. It's the same as in part 2. The weighted sum of 2 and 3 is 5 for A and B, is 10 for F3, and then our error function is 40.5. And indeed, if we run our Python code and printed out those variables, we'd get concurrence with the same values. So then what next? So we configure our inputs to these sample values that we stated earlier and that we used in part 2 when we showed the algebraic approach to backpropagation. And then we've connected up our simple network, these 4 lines of Python code. And then all we have to do to calculate the gradients of the error with respect to S1, S2, S3, the variables that we specifically declared the requires grad equals true parameter on, is merely call this one method on the output function, error.backward. That's it. That's all we have to do, is just this one method, and believe it or not, that computes in the background all of the gradients with respect to those parameters, and does it automatically for us using the backpropagation technique, which we're going to explain in the next few slides how Pytorch does that. So let's just convince ourselves that this works. If we were to actually print out the 3 parameters, our what we were calling levers in part 1 and part 2, S1, S2, S3, and we inspect the .grad property of these variables, we do in fact see the same answers as we had in the previous section, part 2, when we computed these manually. So the partial of error S1 with respect to the the partial of the error of the gradient with respect to S1 is 45, which is what we got when we did it manually. With respect to S2 is 45, which is also what we got, and then with respect to S3 is 90, which is also what we got when we did all of this algebraically in part 2. So merely this one line of code, error.backward, is the magic of Pytorch. This one line of code, this one method, does the entire backpropagation of all of the network of functions for us, and the network can be arbitrarily complex and arbitrarily large. It's just a matter of computational effort at that point, But the fact is, all of the method that we saw to do the gradient descent, to do the backpropagation rather, in part 2, has been hidden from us. It's done in this one method. So what we're saying then is that that one line of code, error.backward, did all of the math shown here. In fact, these were the algebraic expressions that were the outputs of our differential calculus. So there's the actual calculus itself has been done by the dot backward. The algebraic expressions have been constructed using the dot backward, and then they've been evaluated for the actual numerical inputs from the forward pass using this one line of code. So all of that is done in one step, one line of code. So how does Pytorch do this? It uses a inner library, part of the Pytorch framework, called Autograd, which stands for automatic gradients. And this is all written for us, and we're now going to look at how this works. So we said that we connect up our network. So what do we mean by that? We mean that we declare some arbitrary Python code, which is this composite of functions, one function feeding to the next, and so on, and then our final output error function. Now Pytorch records, because we imported Pytorch into this code and we declared these variables to be tensors, torch.tensors, Pytorch is able to record the computation of this forward pass as it computes it. What does it mean recording this? Well, it does that because it then looks at each step that it recorded in the process and turns that into a computational graph, which is a map, if you like, of every single step, every operator and function used to evaluate this network of functions. And here we see it on the right. We've printed out from Pytorch what this graph looks like, and you can see somewhat it represents the equation on the left in Python, but we can overlay it with our Pythonic expressions just to see how it does in fact concur. So ignore for a minute these strange names in the grey boxes like add backward 0, mole backward 0. We can just see generally that the if we just follow one of the paths down like S2 and ignoring the accumulate grad, we can see it's put into a multiplier first. And indeed S2 is in fact multiplied by x11 and x21, and we can see those arrows feeding into that multiply backward to give us the S2 times x21, and then we can follow that down. That adds then with A and B, which are themselves scaled by S3, and then we end up of course with the final output error, ERR. Now because we have this as a graph, that means we can in fact trace the connection of every operation to every other operation, both in the forward and the backward direction, and the fact that we can traverse this backwards is what's going to help us to compute the backpropagation in a computationally efficient fashion. So then how do we do the backward part, the autograd? So to illustrate this, we're going to use a very simple sort of trivial function, some arbitrary code, p equals a times b, q equals sine of that multiplication, i.e. the sine of p, plus a new independent variable c, and r equals the square of q. The square here is the same as saying q to the power 2, but it's easier if we just confine ourselves to a square function when we differentiate, rather than something more generic like a power function. So this is what the graph would look like drawn manually. A and B feed into a multiplier, then the output from that P is fed into a sine function, the output from that is then fed into an add function, into which is also fed the independent variable C, and the output of that is then fed into the square function to give us our final output R. So I hope you can see that this graph very clearly represents the computational steps required to evaluate the composite function on the left. Now, because we've used Pytorch, what happens is that each of these operators in Python, like the multiply, the sine, and the square, imagine the square is a native function for a minute, they are overloaded by an equivalent Pytorch operator or function that has the same mathematical capacity. It's multiplies, or it does the sine, or it squares or adds. Yet that operator, that overloaded operator, is actually also can be inserted as a node in a graph. So this allows us, this is what's doing the recording, because each of these operations in Pytorch can be connected in this tree-like fashion to create this graph. So again, note that the square function is just a convenience that I'm using to show that we intend to raise q to the power of 2, but otherwise in the actual Python this would be a power function. So then each overloaded operator, this is the key thing, in Pytorch has built into it a knowledge of how to do the differential of that function. So for example, if we look at the square function, built into that node, because it's this overloaded function in Pytorch, it also has the inverse, or the differential of the function. So it can do the square function, square the input to give you the output, or it can go in reverse and give you the differential of the output with respect to its input. So the differential of the square function, x squared, is 2x. So you can see that here written. And then that's multiplied by the initial input gradient, which we'll see is nominally set to 1, because the differentiation of a function with respect to itself is 1. So in the chain rule, if we're going to evaluate the chain rule in every single step going up this graph, to bootstrap that or to initiate it, we would just for convenience put the function itself back into the chain rule, and then that would allow us to start with the partial accumulated gradient of 1. Then we can see that the built-in of the add function also gives us a differential. The sine computational node has its differential, so the differential of sine with respect to its input x is cos of x. And then the multiply, you just flip the multiplicands to get the differential of the multiply function. So nominally then, for each of these nodes in the graph, which we have said are Pytorch operators that overload our standard Python operations and functions, there is a dot forward method and a dot backward method. And the dot forward method corresponds to the ordinary mathematical expression that we're evaluating, like plus, add, sine, square. And the dot backward method corresponds to the associated differential equation or calculus. So with backpropagation, or rather Autograd, there's no sort of like finite difference method to calculate the gradients. We actually, if we know it, we have the state explicitly the known numerical operator, the precise operator for the differential. And because we can state this precisely, like the differential of sine is cos, we can do an exact numerical computation, which is what makes this numerically stable and efficient. Now, this is what's going on under the hood, and in fact the actual implementation of this is done at a lower level beneath the Python in C++ in the A10 library, and the Python functions that are overridden by Pytorch are bound to these underlying C++ functions. And indeed you can even define your own custom Autograd functions. If you had some mathematical operator that you wanted to insert into your math, into your network of functions, you could inherit from the Autograd class and then define your own forward and backward methods on that object to insert your own custom Autograd functions into the Autograd library. So if we look at the arbitrary code we had previously, first of all, let's just write out the algebra for this. So dr by dq is going to be 2q, which is the differential of q to the power 2. dr by dc is then 2q times 1, because 2q by dc is 1. And notice how then we're already passing the previously computed step back into that calculation, even though we're showing it moving down the page. Obviously we're actually evaluating this from R backwards, so it's going backwards. And then dr by dp, of course, is dr by dq times dq by dp. We already have dr by dq, which is 2q, and now we compute dq by dp, which in the Pytorch node is already built in. It's the cos function, and we have to pass the input, which is p. So we do the cos of p, and now that cos of b times 2q will give us the partial of r with respect to p. The partial of r with respect to a is again passing that back up and now timesing by b, and then with respect to b is passing that up and multiplying by a. So this is the algebra of the partial calculus, differential calculus, to evaluate this function with respect to the inputs a, b and c. So what does that look like? So on the forward pass, again, we would input torch. We would declare our inputs a, b and c using torch tensors, and here we're going to set them to 0, 1, and so that would give us the multiplication now of 0 times 1 is 0. We then pass that through our sine function. Sine of 0 is 0. We now pass that into our add function, and we also pass in our independent variable 1c, which is set to 1 here. So 0 plus 1 is 1, so q equals 1, which we square, and that's r equals 1. So the code on the left is nominally mapped to this computational graph we're showing here, which we've drawn manually, but it's very similar to what would be involved in the Pytorch underneath. And indeed, if we print out the values of p, q and r, we see 0, 1, 1 in our code, similar to we have in the chart here. So then what is the back propagation? How does that work? So we immediately invoke the dot backward method on the output r. And what's this going to do? Let's have a look. So we said that we bootstrap the process by setting the initial partial gradient of dr by dr, a function with respect to itself, which is 1, because we're going to run this kind of iterative chain rule process up the graph. So we need an input of the current partial gradient into each step. So the input of the partial gradient of the output is 1. Then we can see for the square, the differential of the square function 2 to the power of x is 2x. Or sorry, the differential of the square function x to the raised to the power of 2 is 2x. And then to do the chain rule, we multiply that by g. We have the g is the input of 1. X is set to q, which is the input, which is 1. So we get g, which is 1 times 2q, gives us 2. So therefore, the partial of r with respect to q is equal to 2. So that becomes our new partial gradient, which we can then feed up as the input to the next step, or the parent node in the graph. And here we have an add function. So if we compute now the partial of r with respect to c, that's just g, because it's an add function, meaning a constant. So g is set to 2, which is the input from the previous partial differential gradient accumulation, and so the answer is 2. So now we can also take the same partial gradient that was fed into the add function and go up to the parent function, the sine node. And then that's set to 2. We then multiply by the cos of x, and the cos of x is the differential of sine of x, and x here is the input, which is p, which is 0. So therefore we get g, which is 2, times the cos of 0, which is 1. 2 times 1 is 2, and so the next partial is 2. That then becomes the input to the next parent node, which is a multiplication function. So if we do the partial of r now with respect to a, that's going to be g times b, where g is set to 2 and b is set to 1. The answer is 2. And then if we do the partial of r with respect to b, that's going to be g times a, where g is set to 2 from the previous step, and the input a is set to 0, so 2 times 0 is 0. So then if we print out, you see at the very bottom of the screen there, we actually print out the a, b and c tensors, and we inspect the dot grad property, we can see that they are indeed corresponding here, 2, 0 and 2. So this is backpropagation. Each of these nodes has built in the ability to evaluate the differential of the function using the dot backward method on each of those nodes, which is invoked in totality by the dot backward method on the output, final output R. So that's all there is to it. That's backpropagation, and all this is done for us underneath the hood. So one last thing then. We said that hitherto our functions, our nominal functions, our kind of toy functions we've been using, these partial, these weighted sums, a equals s1, x11 plus s1, x21, are not artificial neurons, they're not perceptron equations. So what happens then if we actually switch to the actual perceptron equations? With an artificial neuron, each input has its own slider, and then we introduce a biasing slider to move the whole function up and down, and then the final output of that sum is put through a non-linear function called an activation function. So we have s11 now times x11, so we have not just an s1, we have an independent parameter or variable or weight which controls the x11 input. We have an independent parameter s21 which controls the x21 or scales the x21 input, and then we have this independent parameter s-bias which moves the whole function up and down. So we have as many degrees of freedom as there are inputs, plus the bias function. And then that whole of that summation is fed into the activation function, which is some non-linear function. This is the part that's necessary actually for universal function approximation, which we mentioned in part 1 of these lectures. So what happens then when we switch from the toy example we've been showing to fully blown perceptrons or artificial neurons? Well, in fact, nothing happens, because the math is exactly the same, and backpropagation, as I said at the beginning, doesn't really care what the functions are so long as they're differentiable. So we just have more sliders to compute gradients for. So now if we look at this one function, we have to do the error with respect to s11, the error with respect to s21, and the error with respect to the bias. And we can simply apply the chain rule, and that goes for the activation function. So the partial of the output of this function with respect to s11 is the partial with respect to the activation function times the partial of the activation function with respect to s11. Similarly for s21 and s-bias. So this is just more algebra, and these independent sliders and the activation function are required to make the neural network actually do something useful, this universal function approximation. But the math in terms of the algebra, the chain rule, and the backpropagation is the same, and so the error dot backward method still works. It's the same, it just works. So everything we've described in the presentation to this point was a rather simplified network of functions that we did that to make it easier to understand and to follow in terms of the algebra and the math and the backpropagation. But converting to fully blown activation functions makes no difference, and indeed we could also name all of our functions, our inputs rather, using the nomenclature we said earlier, x11, x21, and then the next layer could be x1, 2, x22, and so on. So it just works, there's no difference. So one last thing then that is pretty important. So we said that the tensor, torch tensor method allows us to support fully blown tensors, which are the, can be any dimensional, multi-dimensional data structure. And we can exploit this. How do we exploit this? Well, all the sliders for a particular layer can be described by a vector, and both for the parameters and the bias. And all of the inputs to a layer can be described as a single vector x. And then the activation function here, nominally shown as a sigma, which could be the sigmoid function, but here I'm just nominally showing it as sigma. It could be any function, as long as it's a non-linear function that's both a valid activation function and a differentiable function for Autograd to perform and work, do its business. All of the computation here can now be expressed as one single computation. Now, when we evaluate this then as a large matrix calculation, if we did it manually, we'd be doing one step at a time. But the beauty of this is that this can be vectorized such that each of the multiplications, for example, in the dot product are done at the same time. And how do we do that? Well, again, we can use the beauty of Pytorch. If we have an accelerator available, a hardware accelerator like a GPU, then we can merely call the .2 function and move these data structures, the vector s and x, to the GPU device, which is in the software name for that here we're saying is CUDA. And CUDA is the programming model used by NVIDIA to do hardware acceleration of matrix maths or deep neural networks. And so we can move our neural network to the GPU and invoke our backward function and do our forward function on it. And now the entire matrix is done in parallel using multiple cores, math engines. So this is even more efficient now because as we compute in both the forward and the backward paths, we're exploiting the ability to do lots of mathematics concurrently in parallel using all of the mathematical cores or engines on the GPU. And again, Pytorch does it all for you. You don't have to know anything about how that works. Under the hood, it's done using sophisticated math libraries, low-level math libraries written in C++, like QBLAS and a number of libraries that can do the deep neural network calculations for us efficiently. And so we've got now sort of like 2 for 1 here. We've got the backpropagation with the single method, and we can just by merely assigning those values, our vectors to the GPU, we can accelerate that method as well. So boom, Pytorch drops the mic. All of this power, backpropagation, GPU acceleration is done for us. We don't have to have any knowledge of how that works. For the most part, of course, in certain modes of research and, when things don't quite go right, or we're trying to create novel neural network configurations, then we may have to go down beneath these abstractions and see what's going on under the hood. But in principle, that's what Pytorch is for. It's there to do it all for us. So let's then recap what we've been through on this very brief journey of backpropagation. In part 1, we said that a neural network is a configurable function approximator. It can approximate some function in the real world, like, for example, predicting the likelihood of buying a product based upon all of the data we can collect from a website analytics, or the traffic density in a city based upon a whole bunch of sensors around the city. Or we can, for example, look at all of the pixels in a scan of a handwritten digit and then try to search in the function space for some function that will map each of the digits to a probability that it is a 0, a 1, or all the way up to 9. We can then configure our function using what we called, using a metaphor, levers, which are parameters, or in the world of neural networks referred to as weights. So then we have a means to configure our function inside of our neural network, and we're trying to do that to see if we can find an optimal function that represents the relationship between the sample data features and the target variable. So we give it this historical data, the sample, and we measure the function outputs against the expected outputs, against the target variable or variables. And this gives us an error function, a way of measuring the difference between the two, which is also sometimes called a loss function. We then say we want to minimize that error function in aggregate with respect to all of the sample and all of the sample data. And that would then tell us that the model function, the function we've approximated, is somewhat representative of the function that presumably generated the data, because when we try to predict the target variable using our model function, the error is as small as we can make it with respect to what we actually saw in the real world. So we assume we have therefore learned something of the underlying distribution of data and hope that it will generalize to new samples. So this minimizing the function is a classical problem that's been solved for centuries, which is called differentiation, a part of calculus. And we said we cannot differentiate directly. There's no analytical expression for this hidden function. And indeed, if we had even attempted that, it would be intractable. So we don't have some convenient function we can differentiate algebraically and set to 0 to compute the minimum. We said we can compute the gradients using the chain rule, and we sort of showed how to do that in part 2. And we can move slightly each lever, perturb each lever, if you like, in the direction of the downward slope. So we showed how this could actually be done computationally using backpropagation. And then each step that we take, and by adjusting the parameters, the levers, to take a step towards the minimum of our error function, so that our approximate function, we hope, is close to the actual latent function or the target function in the real world. And we called this process of moving down the slope gradient descent. We then showed how we could actually evaluate the chain rule computationally via backpropagation, which is computationally efficient. Not only because we're reusing the computational steps from previous computational steps, but because in the way this is architected in Autograd is that we can actually compute the precise differential equation differentiation rather of each node. And if we can precisely express it, say the differential of sine is cos, we can do very accurate numerical computation. And Autograd is a library within Pytorch that does this all for us automatically. We just eventually call the dot backward method on our output function, our error function, and it just works. It gives us the gradients of the numerical gradients of all of the parameters. And it does this by overriding standard computer operators. For example, the sin x in Python, well, in this case you would have to declare that one as torch.sin, but it's then the equivalent of the sine function in Python, but it has this property: it can now be part of a computational graph and contains within it the reverse function or the differential function, i.e. the cos of x. So each overridden node has this built-in reverse function or dot backward function. And then we can run all of those up the graph concurrently and accumulate gradients, which can be efficiently passed back up this computational graph to compute the partials of the error with respect to every single one of the gradients efficiently, automatically, and numerically stably. So this is the beauty of Pytorch Autograd. So we've been on this journey, showed how we can move from function approximation to minimization of the error via calculus to some computationally efficient method or backpropagation via the Autograd library. So you can go and research these things and look them up for yourself. There's a lot more depth than I've covered here or been able to cover, but I hope that we did actually give you some flavor how each of these sort of 3 layers of abstraction, the high level concept, the mid level math, and then the low level computation come together to allow us to implement neural networks and deep learning. Thank you for listening.